Electrolytic cells. Let's have a look. You may have remembered in the video, Danielle's cell. Again, if you haven't looked at that video, please look at that. It's a prerequisite to this video. The video link is in the description. And we identified this electrode here as zinc. And we identified this electrode here as copper. Now, we also had in this solution zinc sulfate. Now, it's important to note that the zinc sulfate broke up into its respective anions and cations because it's within an aqueous solution. It gets dissolved in water in here. So we can break up that ZnSO4 into Zn as its cation and its SO4. It's anion. So we have these two things floating around within this, within this solution over here, okay? And same thing with this solution here. Rather than zinc sulfate, we had copper sulfate, okay? Again, because it's dissolved in water, it's going to break apart into copper ion and sulfate ion. So that's what we have here. Now, in that video, if this here was a voltmeter, because it happened spontaneously, because Danielle's cells are galvanic cells, they happen spontaneously. So we identified that the electrons come from here and go through the voltmeter down into this electrode, okay? So again, see that video first. But in this video, we're going to be identifying this thing over here not as a Danielle cell, so not a galvanic cell, but rather an electrolytic cell as identified in the title, which means we need to have some sort of power supply. So rather than a voltmeter, let's say it's some sort of battery, okay? I'll just say it's identified as B, okay? So this here would be a battery or a power supply, an external supply that is going to help us reverse, okay? Reverse the reaction over here. So if that is the case, that means this copper, okay, is going to be releasing the electrons this direction. So let's assume it's copper 2, okay? So let's say 2 electrons leaves this electrode, goes through this battery, and then goes into the other electrode on like the zinc electrode here, okay? So this Cu, if it loses 2 electrons, it then becomes what? It becomes a copper ion, okay? Right now it's an atom. Here, maybe I'll just put an S just to identify it easier, okay? It's solid copper, and it's going to become a copper ion, okay? So it just does this, okay? So where is this thing gonna go? Well, of course, it's gonna go somewhere within the solution, okay? Right over there. So let's assume, I'm gonna do it in green so you can see it better. It goes into the solution. Okay, so now it becomes Cu 2+, okay? But remember, this Cu 2+, in order for it to be neutral as the left side over here, it must be canceled out with a 2- or 2 electrons. That'll do, okay? So 2 minus 2 gives you that net 0, same as the left side. So this Cu right over here has released 2 electrons as indicated over here, but it's also releasing Cu2+ as indicated over here. So similarly, it's going to happen on this side too. We have 2 electrons going into this electrode. So I'll write this over here. We have 2 electrons going into the electrode. And what's the electrode in question? Obviously, it's the Zn. So I'm going to write ZnS. But of course, this is not neutral. There's a 2- over here. There's a 0 over here. So we have to be adding Zn2+, obviously, in order to make it neutral, right? So -2 and then +2 gives us that 0, same as the right side. But if we have 2 electrons, that's this one over here, going on to the electrode, this Zn2+, where is it? Because this Zn2+ also needs to go on to this electrode as written out over here. Where is the Zn2+? It's over here, right? In the aqueous solution. It's embedded within this water, right? This zinc sulfate, it's embedded into here. So this Zn2 plus needs to go in, okay? So this Zn2 plus is going to go into that electrode. Okay, so I'm just going to quickly exit out. So there's an X over there. What does that mean now? That means within this solution, what's left? Mostly the SO4 minus, the sulfates. So what is the net overall charge within that solution now? Obviously, it's a little bit more negative because we have a lot of SO4s left. We have no more positive cations. So how do we balance out net neutrality? Well, remember the salt bridge for the S? We use KCl. I think that was our example that we used last time. So if this is broken up into its anions and cations, so that would be a K plus and a Cl minus, right? How would we balance it out? Well, if there's too many negatives in here in this solution, we have to use the K plus, right? The K plus would then go into that solution in order to balance it out, okay? Now, how about on this side over here? Well, we said that there's Cu2 plus, a lot of it within the solution right now. So if it's a little bit too positive, because remember, we still have Cu2 plus here, we've added even more Cu2 plus from this electrode going into the solution, and we still have some SO4, right? But we have more Cu2 plus and Cu2 plus, right? This means it's going to be overall too positive. So how do we balance it out? Well, this Cl minus over here will obviously need to go in and replenish it to make it a little bit more negative so that it neutralizes it out. So to conclude on that note, what is the difference between galvanic and electrolytic? So obviously for the galvanic, it converts chemical energy into electric energy. So this is like within a battery. Obviously, we have a lot of chemicals within that battery, and in order for that battery to become useful to us, it needs to turn it into electric energy so that it's to our benefit. Okay, it happens spontaneously. But a electrolytic cell, the one that we just talked about, okay, requires an additional source of power in order to drive the reaction in the opposite direction. So it's kind of the opposite of a galvanic cell. It converts the electric energy into chemical energy. See, this stands for chemical, right? Let's try this question over here. The electrolysis of molten calcium chloride. Okay, so molten means that it cannot be aqueous. It's just really, really hot temperature. So rather than putting aqueous, we got to be putting just the liquid. Okay, we're just using very, very high heat. And that is going to obviously break it down. And then it's going to make calcium. And it's going to be in liquid form, not aqueous, right? And chlorine, also liquid, not aqueous. Okay, there's no water involved here at all. Now, obviously, chlorine has a 2. It can't exist on its own. It has to be paired, so we are now done. But remember, if this one here can break up into its constituent anions and cations, let's write it out as such. So we have Ca, but of course it has a charge of 2 plus as indicated over here, and it's still in liquid form. And this Cl, okay, there is 2 of them, but of course it needs to be Cl minus because it has a charge of -1 originally. And we can keep these on the side as we see fit. Now let's look at the half reactions. Doesn't matter which one you want to do first. We can maybe start with calcium because it's most on the left side right now. So let's put Ca, 2 plus, and what is it yielding? It's obviously yielding Ca liquid. Now 2 plus over here, so we got to balance it out. So we have 2 minus over there, and we are good. So we are finished in that case. Now let's do the same thing for our Cl. So we're starting off with 2 Cl. Yielding what? It is yielding Cl2. Now this 2 minus over here is on the left side, so we got to be putting a 2 minus over there as well to balance it out. in terms of its charge. So now it's done. Let's identify which one is the anode and which one is the cathode. Obviously, cathode is when it loses electrons. Okay, so obviously that's what we see over here. So let's say put this one over here. This here is the anode. And obviously it is the negative electrode, right? This one here would then have to be the cathode, which makes sense because there are 2 electrons on the reactant side, not the product side. So we can add these all together. So we have a Ca2 plus our 2 electrons. What else do we have on the reactant side? We have 2 Cl, all yielding our Ca L plus Cl2 L and 2 electrons. Cancel out the 2 electrons, cancel out the 2 electrons. What do we have remaining? We then therefore have our Ca2 plus our 2 Cl minus, yielding our Cal and our Cl2L. That's the answer. Okay, let's try this question over here. Looks similar, right? But this is a little bit different in terms of our statement at the end because it says now at the negative electrode. And you're probably thinking, isn't the negative electrode the anode? Okay, that we're kind of used to. Okay, and how about this positive electrode? Is this positive electrode the cathode that we're kind of always talking about? Let's check. So let's write out our lithium bromide. And of course, this is going to be molten. Okay, so we just have it in liquid and then we break it up into its liquid lithium because we're going to be heating it so hot. Okay, so lithium is eventually going to be able to be extracted straight on its own, okay, and break its ionic bond between bromine. Now, of course, we know that ionic bonds are extremely difficult to break apart. If you don't know why, please see the previous video, link is in the description, about inter and intramolecular forces. And then we have our Br has to be 2 because it is a diatomic molecule. And it's going to be liquid. Okay, so of course this is going to then break up into anions and cations. So we have Li, of course, it has a charge of 1, and we have bromine has a charge of -1. And let's just continue to write what we see on the product side. Okay, now do not forget to balance it. Okay, obviously there's 2 on this side, there's none on over here, there's only 1 over here, so we're going to be putting a 2 over there. I think we are good. So now let's continue to do what we need to do, our half reactions. Let's start with maybe our Li, its half reaction. Now there's a +1 over here, so we're going to put a -1 over here in order to balance out neutrality, just like this one over here. And then we can do our 2Br minus, yielding our Br2. 2 electrons over here, so it's a 2 minus charge over here. We're going to be putting a 2 minus over here as well, so let's put 2 electrons. Now let's figure out our anodes and cathodes. We know that if this one here, the electron is on the reactant side, it has to be the cathode. And if the electrons are on the product side, it has to be the anode. Nothing's changed so far, but now we have to identify it differently. Whenever we're dealing with a negative electrode within the question, we have to assume if it's in a electrolytic cell, so it's written in the question, there is electrolysis going on, it is reversed. So even though this is our cathode end, this cathode now doesn't behave as a positive that we're kind of used to all the time. We now have to know that it now behaves as the negative end, because now, like the previous example I just showed you, right, the Daniell cell, if changed to an electrolytic cell, reverses direction. It goes the opposite way. So rather than it acting as a positive, so it receiving electrons, it's now going to act as negative. So it's going to be a loss of electrons. It's going to transfer electrons away. So this cathode acts as a negative electrode. So that means our anode over here, our anode then becomes the positive end. Okay, so that's where it's going to be receiving the electrons now. So now that we have identified A and B, now let's finish off with C, okay, the net ionic equation. So of course, this one over here is not enough to become 2 electrons. So now, obviously, this 1 electron over here is not the same as 2 electrons there, so we can't cancel them out. So what we're going to do is multiply the whole thing by 2, okay? So let's start with this one over here. We'll have 2 Li plus 2 electrons plus 2 Br minus, yielding our 2 LiL plus Br2 L plus 2 electrons. Let's cancel out the like terms. We are good. Okay, so now we're going to finish off with our statement here. We have 2 Li L plus 2 Br minus L, 2 Li L plus Br2 L. That's it. That's the answer. So any normal galvanic cell that you're kind of used to, so I'll just put here in quotation marks for normal. So if we were, let's say, dealing with zinc, because obviously zinc is the one that is losing electrons, so we can just put oxidation. Okay, this zinc oxidation, it happens at the anode, right? So it happens at the anode. So if you were to look at its half reaction, it would be zinc. Obviously, it is a solid over here. It becomes a Zn2 plus and releases 2 electrons. We would identify this if we looked at its voltage, its E standard, as negative 0.76 volts. Okay, so again, we know whenever it's oxidation, loss of electrons, okay, that's why it's pertaining as a negative in front of the value. If we were to look at copper, and that would just be the reduction end, we treat it as the cathode. Okay, and of course the electrons would then have to be on the reactant side. So if we have Cu2 plus, it would have to be paired with 2 electrons, right, for neutrality, and then it's going to create our Cus. Okay, and in terms of its E standard, I'll just give it to you. It is it is 0.34 volts. So if you wanted to find the standard potential, right, obviously you would just be doing 0.34 volts minus 0.76 volts, giving us 1.10 volts. Okay, this 1.10 volts, it is a positive value, which means that it's going to be spontaneous. If you need to know more about spontaneity, see the video link in the description where I talk about spontaneity in great detail and at length. But if we look at something that we're not kind of used to, so something like an electrolytic cell that we're not familiar with, let's say we have our Zn, again, our zinc, okay? This time it will not be oxidized, it's actually going to become reduced. Okay, and our Cu over here, okay, it's going to be flipped, right? So then it's going to become oxidized. So our ZnS, okay, we had it on the left side up here, okay, and it is turning into its products that you see there on the right side. It's going to be the opposite. It's now going to go towards the Zn. It's going to start forming. So the whole thing just gets reversed. Okay, I'm just writing it out as I see fit up here. Okay, it's just turning towards the left side now. So its E standard, rather than it being negative 0.76, it's now going to be positive 0.76. And that means this one over here, because it is being oxidized, it is losing electrons. That means these 2 electrons that we kind of see up here, okay, if it's being lost, it needs to go in that direction. It is being produced, it is being yielded. So I can keep this Cu2 plus over here, okay? Obviously for neutrality. That means this Cu is going to stay on this side. It's just the whole thing, though, is just now going towards the left side now. And now the E standard, rather than it being 0.34, is now going to be negative 0.34 volts. So again, formula is always the cathode minus the anode, right? Technically, this is still the cathode, but the cathode is now being reversed where it's becoming negative, right? It is being oxidized. And this side is still the anode as indicated up here, but now rather than it being oxidized, it is now being reduced, okay? So you can think of this side as being kind of positive now when it's usually negative, and you can think of this side as being negative now when it's usually positive, right? Because we know that anodes usually pertain to negative, and we know that cathodes usually pertain to positive, okay? It's being flipped. So now we just have our cathode, our negative 0.34 volts, okay, minus our anode 0.76 volts. What do you end up getting? You obviously just end up getting negative 1.10 volts. Obviously this is not going to be spontaneous. Hence why you need that power supply that we did in our illustration, okay, to push it in the opposite direction, the electrons. So these are the 3 green questions of the day. Obviously, this is the first one, this is the second one, this is the third one. Please pause the video, try these on your own, and I'll be giving you the answers shortly. This is the answer to the first question. This is the answer to the second question. I'll slowly scroll down. And this is the answer to the third question.